Look at this integral. It runs all the way to infinity, has 2 cosines, and an x squared in the denominator. Yet the entire thing equals exactly pi. The trick is not to integrate it directly. First, use the product to sum identity for cosine x times cosine 2x. This turns the numerator into 1/2 of 1 minus cosine x, plus 1/2 of 1 minus cosine 3x. So the original integral splits into 2 integrals of exactly the same type. Let j of a be the integral from 0 to infinity of 1 minus cosine of a, x, divided by x squared. Then our integral becomes 1/2 j of 1 plus 1/2 j of 3. So now the whole problem is to understand j of a. Since we only need positive values of a, make the substitution u equals ax. The scaling is simple. J of a equals a times j of 1. So everything reduces to finding j of 1. Now integrate j of 1 by parts. The boundary term disappears. At infinity, 1 minus cosine x stays bounded while x grows. And near 0, 1 minus cosine x behaves like x squared over 2. What remains is the integral from 0 to infinity of sine x over x. So now we have reached the famous Dirichlet integral. But instead of just quoting its value, let's derive it. Introduce a positive parameter s, and define d of s as the integral from 0 to infinity of e to the minus sx times sine x over x. As s approaches 0 from the positive side, d of s approaches the Dirichlet integral we want. The exponential factor damps the oscillation and makes the next step easier. Now differentiate with respect to s. The x in the denominator cancels, giving d prime of s equals minus the integral from 0 to infinity of e to the minus sx times sine x. Call this new integral I of s. To evaluate it, integrate by parts twice. After the first integration by parts, I of s equals 1 over s times the integral from 0 to infinity of e to the minus sx times cosine x. Call that integral k of s. A second integration by parts gives k of s equals 1 over s minus I of s over s. So I of s equals 1 over s squared minus I of s over s squared. Solving for I of s gives I of s equals 1 over 1 plus s squared. Therefore, d prime of s equals minus 1 over 1 plus s squared. Integrating with respect to s gives d of s equals pi over 2 minus arctangent of s, because d of s approaches 0 as s approaches infinity. Finally, let s approach 0 from the positive side. The damping disappears, and we recover the integral from 0 to infinity of sine x over x equals pi over 2. That means j of 1 equals pi over 2. And because j of a equals a times j of 1, j of a equals a pi over 2. Now return to the integral we started with. We had 1/2 j of 1 plus 1/2 j of 3. So this becomes 1/2 times pi over 2 plus 1/2 times 3 pi over 2. And everything collapses to pi. An integral that looked almost impossible at first ends with one of the simplest constants in mathematics.